Hello, my name is Simon Foley. I'm from Vishay IC Market Development Team. Today, I'd like to do a live simulation of PowerCAD. I'd like to show you how it works, how to gain access, and how we can help a designer, power designer, with his power conversion. So let's look at access first. You can type into a search engine vishay.transim.com/landing, into a search engine Vishay PowerCAD, through a Vishay page from one of our distribution channels or from our own website. So in our web page, you select products, microbuck, and then it'll give you a widget where you can start the design on the top. Change your parameters here and gain access straight away. There's a link from design tools and also through the datasheet itself. In the datasheet, you find the link on the top left of every microbuck datasheet. So let's look at PowerCAD. What is it? It's a free online simulation tool that allows the designer to successfully accelerate the circuit design and enhance confidence for the first-time success. But what does that mean? It really means that the engineer can customize, analyze, and finalize his design. Okay, what's in PowerCAD? We've got online schematics, a calculator that calculates peripheral components, and I'll get into that a little bit later. It's got functional analysis tools, simplest simulation where you can look at transients, startup conditions, etc. View waveforms as you would in a lab condition with an evaluation board. It can calculate efficiency, power losses, and thermal analysis, which is pretty unique to Vishay. It'll give you a report of bill of materials, and also you can save a full design report at the end. You can send it to yourself, colleagues, or you can send it to one of our local or your local FAEs for technical support. So let's start the design. First thing you get when you click into it is the disclaimer. And what this does, you can agree, if you want to continue, agree that we take no liability for any changes, errors, inaccuracies, etc. So I'm going to say agree. The first thing you should do is register. Now, by registering, you register into the Vishay website, not PowerCAD, to the Vishay website. And that then will allow you to save your design, retrieve it, etc. So I'm going to go into login. If you haven't already, you need to register. I've already put my details in, so I'm going to log in. And it'll take me to the first screen. And this is it. It'll take me from, or I'll take you from left to right. I'll take you from part selector, configuration, analysis, bill of materials, and report. So there's a flow through the simulation tool. Again, on the top right, you'll see my designs, share design, save, and you can start a new design as well. So you can save your design as you go through. And I recommend saving this maybe every 5 minutes, just in case it logs you out. So we're on to the first screen, which is part selector. You've got a widget here and you can select whatever parameters you want. I want to say 4.5 to, let's say, 36 volts here. I want a V out between 0.8 and, okay, let's say 5.5, and a current out at 3 amps. And as I change the filter here on the widget, it will change your configuration. You will give me the part numbers that I can select from this. And in it, you can select data sheet to give you your status, whether it's new, active. You can get into the datasheet this way, and it'll give you your parameters, key features, etc. Then you can look at your filters in more detail. You can select in integrated magnetics, which is our micro brick family with the integrated inductor. I'm not going to do that today. I want scalable, family scalability, and what that means is the parts that underneath this, all these are pin for pin. They're all the same package size. Scalability means, for example, if I want to design 3 amp, I design for 3 amp, and the system designers come back and they say they want more than 3 amps, they need 5 amps or 8 amps. You can change this one, for example, and change it with an 8 amp. You can change a 3 amp with a 5 or an 8 amp. You don't have to change the footprint of the PCB. It's exactly the same. So that family scalability, and that's pretty unique to Vishay. I want to select power save mode because I want light load efficiencies. There's a drawback in this that for the improvement in light load efficiency, what it means is the frequency will fold back at light loads going into diode emulation mode. But you do get a much improved efficiency at light loads. There's an option here for PM bus telemetry. Now, PM bus telemetry is becoming more and more popular in telecom infrastructures, digital servers, for example, and in high-end industrial. It allows the designer more flexibility and to optimize his design, giving live performance monitoring and failure analysis. But I'm not going to do that today. This is a nice filter here because you can select active, new, or pre-release. Now, if you go for just pre-release, you'll see what we're going to be releasing in the next couple of months. So you can still simulate it. You can keep an eye on it to say, okay, what's Vishay got coming out in the next couple of months? So you can simulate it just before we bring out evaluation boards. So I'm going to click active and new today. Going on to the bottom list of filters here, you can select temperature range. And the 150 is for our automotive range, which we'll be bringing out soon. You can select what frequency you want to set up to 4 megs. Additional features, internal compensation, for example. I'm not going to select any of these today. Package size, if you want to filter and drill down to specifics. And your protections, over current, over temperature, over voltage, etc. So from this filter set here, it will give you a list of parts you can choose from. I'm going to select 3 amp, as I wanted to earlier. I'm not going to go into the data sheet, but I could, if I wanted to, look at the data sheet. I'm going to go into the design tab. This then will take me into the configuration. So I've done the part selector. I'm now into configuration. And in this screen, you've got the features, which is taken from our data sheet, up to 55 volts, 3 amps. I can then set my parameters, which I'll do so in a moment. The operating modes, which you find from the data sheet, power save mode, internal, external regulator, and a description, again, taken from the data sheet. Now I'm going to start by clicking in my parameters on 24 volts, typical industrial spec, minimum 18 volts. If I type something that's outside the bandwidth of operation, what it will do, give me a pop-up window and suggesting the range that I can choose from. So I'm going to select 18 volts minimum. I'm going to select 36 volts maximum. I'm going to select a V out of 5 volts. I want to switch to 300 kilohertz, but you can change if you wanted to, up to 2 megs. Current limit, soft start, etc. I'm not going to change this. In power save mode, I've set power save mode enable because I want light load efficiency. I want to enable the internal LDO. I don't have an external rail for this design, but I could have if I did have a 5 volt external rail to improve efficiencies, I could disable the LDO and do it that way. In power save mode, I've got an option of ultrasonic mode. If I select disable, it could fold back at light load into diode emulation mode, fold back below 20 kilohertz inside audio range. I don't want that. I want it to be outside audio range, so I'm going to say ultrasonic. It should fold back above 20k. Now I've got show advanced here. Now, by going into this, the nice thing is that if you're a novice, you don't have to go into the advanced. You can just select whatever you've selected here, your conversion specification. But if you are advanced and you want to change things, you can change your output caps, for example. You can say, okay, I want 50% ceramic, 50% electrolytic, and you can select your bulk caps or your ceramic caps. On this instance, I've selected 10 microfarad, 100% ceramic, and I'm not going to change that. Again, in advanced, you could go down and you could select your DIGT for the load, or you could change your tolerance, your ripple percentage, your V out ripple, and your startup voltage to it. So you've set your parameters, you've done the part selector, this is the configuration you've configured. You now want to analyze, but you press the create design. So you're now moving on into the analysis part of it. We continue with the simulation. Again, what I would do as I go along, I would save the design. Once it's finished with this window, I will save the design as I go along, just in case I lose anything. And then from the analysis, you can go into efficiency and power losses. You can run simulation where you can look at load steps, where you can look at how the output voltage is affected by a change in load. That's what we mean by load step. And then you can look at the simulation results. If anything changes as you go along, for the parameters you set, on the previous screen I set 3%, it's now going to change it to 0.05. So it's a better output ripple. And tolerance, I've selected 2%, but it's going to give you 1.87. So it'll tell you what changes it's made in the simulation tool from your parameters you set. Then click off that. This then will give me my schematic, and from the schematic it'll give me my list of components, peripheral components, and the values. Now, the benefit of this tool is that the designer doesn't have to calculate from the datasheet all the values for switching frequency, for example, your compensation loop, your output inductor. This will calculate everything from the parameters that you've set in from your conversion. The first thing I'm going to do now is save my design. I'm going to save it into PowerCAD. So PowerCAD 1. And I'm going to save that. So that will come up PowerCAD 1, and I can make notes as well. You can, on the right-hand part here, from the right-hand part here, you can shape tools. So you can draw, you can text, you can add text to this as well. And when eventually, then when you do save it in report, your additions from shapes, text boxes, etc., will upload images will be included in the schematic. In this schematic, you see voltage probes and current probes throughout, and you can change any value by double-clicking. So double-click any value here. So you can double-click the inductor. Okay, this gives me the inductor value, suggested inductor value. I can go here and I can change the parameters that I want. Now I can change the DCR that I want, apply filters, and it will give me a list of inductors. In this instance, all Vishay inductors, the peripheral components we do choose, all Vishay if we can do it. So we select Vishay as much as possible, and I can select whatever inductor I want with the part number and the value, the inductor's value in the DCR, for example. You can also go into user defined, and you can select the inductance DCR without part numbers, just generic DCRs, inductance, and current ratings if you choose to do so. On the top left, then we've got the phase margin, so we'll give you your stability of the loop. Anything above 50 degrees is normally pretty good. Crossover frequency, looking at the speed of response of the loop. Your phase margin and crossover are all determined by the RC here, your compensation loop, which is calculated for us, saving a lot of time for the engineer. We selected 24 volts to 5 volts, 3 amps out, and frequency of 300 kilohertz. The next thing I'm going to do is I'm going to look at two things. I'm going to look at efficiency and power losses, and I'm going to look at the simulation. So I'm going to look at the efficiency I've set for this parameter, but I also want to look at load regulation. I want to see how the load transient affects V out, to see what the stability of V out is and how much it droops, the output voltage 5 volts, and how quick it responds. I'll take you through that later. I'm now going to look at efficiency and power losses. Now this could take a minute or 30 seconds up to a minute. What this will do now is it will take me into a screen, an efficiency screen, where I can look at the efficiency, I can look at the settings, and I can look at the response from an efficiency point of view and a power loss point of view, and also a temperature point of view as well. Now, as I said earlier from one of the first screens, we have efficiency, but we also have a thermal simulation tool integrated into PowerCAD, which is quite unique to Vishay. We can look at the parameters, the temperature, power losses through the load, and so we can look at it from 0 amps up to 3 amps. So this is the screen we've got here. So we're looking at efficiency and power losses. We're still in analysis. I can change this from dark to light if I want to print out or save it for save ink, and go back to dark here. So your marker, you see a marker on the efficiency moving left to right here. This is the efficiency response. You can, if you wanted to, look at, you can zoom in if you wanted to as well into this to get a more detailed view of the efficiency at light loads up to 3 amps. Reset zoom as well. It's got a logarithmic scale, and it's got a power curve scale as well, so you can look at the power losses through the range here from 3 down to 0. These are the operating conditions here. So I've got 24 volts to 5 volts. My ambient I can change as well, but it's 25 degrees. Airflow, I can add airflow into it. I've set 300 kilohertz, 0 amp to 3 amp load. This is the performance and thermal analysis here. Now the thermal analysis is broken it down into inductor, high side, low side, and IC, and give you your temperature and your power losses. And the diameter of the disc here will change accordingly. The more power loss, the bigger the diameter, and the lower the power losses, the smaller the diameter. You break down the losses in DCR, ACR core losses, ESR losses, dead time, crossover. You break down all this and you give the operating profile as well, the efficiency, your switching frequency, R on high side, R on low side, your ripple, etc., etc. And that will change as you change the marker here. So if I go up to the 3 amp towards the 3 amp here, this is full. So you see your total power loss there. And as you change from 3 amps, the marker, you move it down through to 0, it will change your parameters, it change your load. You see in the performance here, you see the load efficiency change as you go along. So you can pinpoint any part of that graph and look at the load current, the efficiency, the temperature, the losses, and break down the losses here and the switching frequency, etc. A nice feature of this screen is, again, I would go up and save again before you change anything. You can set a reference, so that's set, and you can change any of these operating condition parameters. I'm going to, the thing I want to look at now is I want to see how that compares, how this conversion spec compares at 300 kilohertz to 1 megahertz. I want to run the tool. So you don't have to go back to the start. You can stay here and compare it on this screen. And what this will do is it will give me a graph here, which is going to be slightly lower efficiency at 1 megahertz, and I'm going to compare it against this efficiency here, which is at 300 kilohertz. And from it again, I can then look at the losses. I can do exactly the same by looking at the losses, which is now set at 1 meg, the efficiency and the losses and the temperature. Once I've done that, I can then show a bill of material compare, and this will show a bill of material, how the bill of materials would change from what I had set before, the 300 kilohertz to 1 meg. Could take a little time, maybe up to a minute to run this as well. So once I've done this, I'm then going to go into the run simulation, and I'm going to look at how the output voltage is affected by a load step of 0 amps, 0 amps, up to 3 amps to see the stability of the system. Once this gives me that, there we go. So this is the reference. My reference is at 300 kilohertz. The yellow line here is now the efficiency at 1 megahertz. And I can do exactly the same here by moving my marker from left to right and looking at this. This is now the active. This is what I'm now seeing with thermal analysis, performance of it, and this is on the yellow line. It's a great way to check it. And then I can go into bill of material compare, just to look how it compares. And this will give me what I had set at 300 kilohertz against this second column here, which is set at 1 megahertz. And if I just look at, only show the differences, what's changed in the schematic, it won't actually change the schematic, but it'll give the bill of materials. You give me changing the inductor from 15 microhenries to 4.7, as you'd expect. In increasing the switching frequency, the inductor value would reduce anyway. Your switching frequency, external resistor set, it changes from 88.7 to 26, as it would from the calculations in the data sheet. Okay, go back there. I can go back to view the design at any time, and that will take me back to my schematic diagram again. So I've looked at this. I'm not going to look at simulation results yet because I haven't run it in simulation. So I'm going to open this page. From this, then I can look at steady state, load step, startup. Now, load step is an output load change from one current level to another current level, and I'll do that in a moment. I can, as I said on the schematics here, you've got voltage and current probes throughout. So you can look at your scope captures, and this is where it takes the measurements from. Scope captures, I can look at that. So I can change my scope probes, and I can move the scope probes. I can relabel them, etc., etc. I don't need to do that in this case. I want to look at load step only, but you could look at steady state and startup. And you could change the load here from 0. I'm going to look at 0. You can't put 0 in, but 0.1 amps to 3 amps. I've got a load step of 3 amps and a period of 500 microseconds. So that's what I'm doing. You can change your delays and everything if you want to fine tune the load step here. You can also change your V-in supply. You can look at pulse voltages as well. So you can look at line regulation and load regulation. I'm just going to look at load regulation here. I'm going to set this up. So I want to check the box load step. I don't want to look at steady state startup. I only want to look at this. I've set my parameters, and I'm going to run the simulator. And what this will do is, from scope probes on the schematic, it will give you your scope captures as you would in the lab. And you can see up here, you can see it moving from left to right to show how far it's got to go. It will still give you your phase margin, UV and V out here. This could take up to a minute, 30 seconds to a minute, depending on your speed of Wi-Fi. Once it's done this, I'll take you to some of the captures we see. Okay, it's almost opening. Right, from this one now, you see the scope captures from output. You could look at input, IC, and switching. For purposes of this exercise, I only want to look at the output, and I want to look at how the output voltage changes or is affected by a change in load step. So I don't want to see I supply, so I'll get rid of that on the right-hand side. I don't want to see the output ceramic current either. I want to see I load, which is the black line here. And I load goes from 0 amps up to 3 amps here at this point. V out is up here. A little bit difficult to see at this time, so I'll explain that a little bit more in a moment. And I also want to see your inductor current as well. So the red is your inductor current that is switching up here. And this, the frequency, as you would expect, with constant on-time topology, increases with the load step and reduces with zero current, with the lower current. So what I want to see is this. I want to see how the output changes with a load step of 0 to 3 amps. And this is the thing I want to see here. So you can either zoom in, or you can change your scale of your axes by going into this here. But there's a nice check button on the left-hand side here, which is auto zoom, auto scale, and it will scale it to look like this is exactly what I want to see. So this button here is a nice little cheat to go straight to auto scale. Again, it will zoom in on everything. It will look at your inductor current, your load step in black here, which is 0 to 3, and you look at the output voltage. And you're looking at, I want to see how this V out at 5 volts is affected by the change in load. On the left-hand side, I've got select mode. So if I press that, I can draw a box and zoom in. I can drag here. If I press this, I can drag left and right, zoom in and out. I can go forward, backwards, etc. I can download and save a file. And I want to see, the next thing I want to see on this one is the droop in voltage and the speed of response till it settles again. And as a normal scope, you've got markers here. So I want to set top marker, each one to midpoint here. Okay, so that's 5 volts, as was set. And I want to check the bottom marker here to the bottom here. So this is the droop, the maximum droop. It goes to minimum voltage. So 5 volts to 4.94. That's the droop you get in V out with a low step of 0 to 3 amps. And to be more accurate, I can go down here and I can see V out here on the bottom left. Marker 1 is 5. Marker 1, sorry, is 5 here. Marker 2 is 4.94. But if you select this and you go delta H markers, it will give you your delta here. So 58 millivolts droop with a load step between 0 and 3. It's exactly what I'm looking for. Time-wise, I can go here and I can select your vertical marker here, the time of the load. I can do the same as you would with the digital scope. I can look at this and say, okay, it will settle at this point here. And there's the information on time, V marker 1, V marker 2. And again, I can do a click on this one and I can look at delta V marker 1, V marker 2 here. This will give me the time in seconds here to settle. So this is the settling time from when the transient occurs to when the V out settles back to 5 volts. Now, if I carry on through left to right and I select bill of materials, etc., it won't save this. It won't save this amended screen here, this amended scope capture. So what I need to do, and I think it's a nice feature, is include in report. So I want to include in report, and I'll select that to V out, and I'll apply. And it'll say, do you want to overwrite what was there before? What was there before was I supply and ceramic current as well. I didn't want to see that, so I'm going to say yes, I want to see that. And then I can go into simulation results, and it will give me my simulation results here. It will give me transient response, output, input, IC, switching, etc. And that will be included in the report at the end. I could, if I wanted to, go back to look at view design, which would take me into the schematic as I saw before. So I've done that. I've looked at the efficiencies and the losses. I've looked at my transient response with the load step. And then, again, I want to save. I can save again just to make sure I don't lose anything. And the next thing I'll do is I'll go into bill of materials. And this will take me into the bill of materials page. It'll give me a list of part numbers and the values and the description, the manufacturer. We use as much Vishay as we possibly can, and we use an alternative if we don't have something. And you see here in stock and price. So it is a nice way of looking at stock levels if you want to order. So you can select this. In this one is select Mauser. You can select Farnell, for example, Network, and you can look at what each catalog distributor will have. So on this one, there's nothing available. I'm going to select, just for curiosity, what element 14 has, and you can see on this some are in stock and there's a price. I can also download an Excel bill of materials as well and save it onto my notebook if I need to. So I've done that, and the next thing I'm going to do is go up to report. So I've done my simulation. I've got the results I want, and I'm going to go into this. This is my report. It gives me the configuration I've set. It'll give the bill of materials. Also, it'll give me the schematic, It'll give me the bill of materials here, and it'll give me my scope captures from my analysis here. Efficiency and power losses. And it will give the disclaimer as well. So everything's here that I've looked at earlier. I can print off, I can save as PDF, or I can share my design. And if I share my design, you can email it to Vishay Tech Support with a comment. You can email it to a colleague, or even email it to yourself as well, so you can look at it. And there's an option here for permission to read write from the person you sent it to, and we can send it back to you with any amendments. Thanks very much for listening.